Welcome back to my kitchen. Okay, so here I have a blood oxygenator. Well, actually it's not a blood oxygenator. It's just a cutting board that's acting like a ramp, but it works similarly to how some blood oxygenators do. So fluid is essentially pumped up to the top of the oxygenator, and it just trickles down the ramp in a sort of flat film. And you can see here, the fluid's basically moving down the ramp. And you can imagine the degree to which blood is oxygenated is determined by the thickness of the film and also the time that the film spends in contact with the air as it moves down. So we might ask ourselves, how thick is this film? As a function of how much flow rate we have going down, how much time, what is the velocity at the top, and also maybe what is the shear stress that the blood is encountering when it undergoes this process. And we can model this as bioengineers, as fluid mechanicians. We can predict some of these things, like how thick the film is and how fast the fluid is moving, based on some known properties of the fluid, as well as some geometry of the system here. So, let's get started. So, although I prefaced this lecture with a cool live demo and example problem of a blood oxygenator, where fluid essentially flows down a ramp pulled by gravity, we need to take a step back and first consider a new problem-solving approach that we're going to use for to actually derive velocity profiles for things like this. So what does that mean? We basically are going to use a new problem-solving approach to derive velocity profiles for what are called one-dimensional flows. And some key characteristics of one-dimensional flows are as follows. Well, so we'll talk about what exactly makes a flow one-dimensional in just a minute. So what are we going to do with this lecture? Well, first we're going to talk about what what it means for a flow to be one-dimensional. Then we're going to talk about this new problem-solving approach that can be used to derive velocity profiles and other interesting things for one-dimensional flows, and that is shells. So we'll basically say, hey, what is this new problem-solving approach? So what is this new problem-solving approach for shells? And if anytime we sort of get a new problem-solving approach, I like to explain to people like why we might need this, right? I'm not just being like, hey, here's some cool new math that makes me feel really good when I lecture about it. No, it's like I want to give you tools that enable you to do new things, right? We can sort of imagine we're an RPG character progressing through leveling up and all that stuff. What new skills do we get after we do this level up, right? So what can shells give us? What can this new problem-solving approach of shells give us that our old problem-solving approaches can't do? So and in particular, I'm going to contrast shells to what I'll call macro control volumes. So what can shells give us that macro control volumes can't? And we'll sort of compare and contrast these two problem-solving strategies. Once we've kind of prefaced these sort of general ideas, general concepts, new problem-solving strategy, we'll then proceed with the example problem that I prefaced at the beginning. So we'll set up our blood oxygenator problem, and we'll sort of give ourselves some goals and also clearly describe what knowns we have in this problem. So we'll talk about goals, knowns, etc. We'll sort of lay out all the information we need to describe this flow, to sort of derive what's going on with this flow. Then I'll outline 6 steps for what I'll call shells problems, where we're basically, the blood oxygenator problem is going to be one example of a shells problem, where we're attempting to derive velocity profiles and then use the derived velocity profile to get cool information. So there are basically 6 steps. So for those of you who like to have a clearly laid out methodology for solving problems, today's your lucky day. I'm going to outline 6 steps for solving shells problems, and those 6 steps will be too much to cover in the lecture today, but we'll do steps 1 and 2. We'll do steps 1 and 2 in this lecture, and then 3 and so 3 through 6 will be in the next. Will be in the next lecture. So that's the plan. So let's talk about what it means for a flow to be one-dimensional. So the key thing about 1D flows is there are sort of 2 characteristics of them. One characteristic is that if we choose our coordinate system properly, it means if we choose our coordinate system properly, fluid only moves in one direction. So fluid only moves in one direction. Huge One Direction fan here. The band, I could take it or leave it. But fluid only moving in one direction for solving fluid mechanics problems, that's my favorite. Because that is related to this flow being 1D. So if we choose our coordinate system properly, fluid only moves in one direction, i.e. in the direction of one coordinate. So, and then also a characteristic of 1D flows is that, if we sort of describe things this way, variation in this velocity, that the flow moves in only one direction, and variation in this velocity only occurs along variation in this velocity only occurs along one coordinate. So there's a lot of words here. Let's describe things a little bit more visually. So for example, let's talk about pipe flow. That's fully developed. That's sort of in a long tube. So pipe flow that's fully developed. So let's say I had some long tube, something like this, and let's say I chose a z r theta coordinate system. And if you have pipe flow that's fully developed and laminar, you typically end up with this parabolic velocity profile that we encountered, earlier, where the sort of clouds opened up and Professor Lennon's face told through and told you what this velocity profile was, and then the clouds closed back in. And in this case, we basically have a velocity in the z direction that's not 0, and velocity in the theta direction. We don't sort of have we don't have flow kind of swirling as it goes down the tube. So there's no velocity in the theta direction, nor is there any velocity in the r direction as well, right? So we don't have flow kind of exiting out of the sides of the pipe, nor do we have any flow swirling around. Those two things basically aren't occurring. We have flow just going in the z direction, and furthermore, this flow that's going with only in the z direction is a function of r
only, right? So it's like we don't have different velocities at different theta positions as long as we're sort of all at the same radius from the center line of the pipe. So this pipe flow that's fully developed in laminar kind of checks both of these boxes here. We have fluid only moving in the z direction, and if we're sensible and choose an RZ theta coordinate system, variation in the z velocity occurs only in the r direction. Let's give another example of a one-dimensional flow. So imagine I have, so this is one example. We have another example right here. So imagine I have a sort of a cylindrical hole where it's solid on the outside, and then I have a cylindrical shaft that's inside here, and then I have fluid in the gap between them. Fluid in the gap between them, and this shaft, this inner shaft is basically rotating. And this is, so I basically have a spinning shaft inside of a stationary housing. And this is an example of sort of lubricated journal bearings that are used in a lot of machines. So, machine bearings often look like this. And then also, sometimes people intentionally design devices like this where you can squirt whatever fluid you want in between these two things and use it to measure viscosity of fluids. Right, so you can basically use the fluid as a lubricant between a part of your machine that's moving and a part that's not, or measuring the you can squirt some fluids in and you can basically measure how much torque it takes to smear the fluid around. So if we think about how fluid is moving, inside the system that looks like this, the fluid immediately adjacent to the moving cylinder kind of needs to move tangentially along with the cylinder, whereas the fluid next to the wall isn't moving very much at all. And we kind of have this velocity profile that sort of develops between the two. So if I were to characterize this system, I might, for example, make my use an r theta and z being out of the page coordinate system. And in this case, I would say vz is equal to 0 because I don't have fluid that's sort of creeping out of the page as this thing spins around. I might say my v theta is not equal to 0, and my vr is equal to 0 because I don't have any fluid sort of creeping out of, being forced through the walls of the solid cylinder or the solid housing. And in this case, so essentially I only have velocity in the theta direction, which is basically saying the fluid particles kind of follow in circular paths along with the surface of the spinning inner cylinder. And in this case, velocity varies. I have a fast velocity here and no velocity at the stationary outer part. So in this case, we have some non-zero theta velocity, and it's a function of r only. So and it turns out that we get 1D flows even in cases where we don't have cylindrical coordinate systems. But I just use these to emphasize that it's not necessarily that the fluid is only moving in one direction, because I have fluid moving up here and down here. But if I carefully choose a coordinate system, I might get lucky in a way where if I sort of define my coordinate system in a clever way, fluid is indeed moving only in the direction of one coordinate and varying only along some other coordinate. So that's the key the key thing that sort of defines a 1D flow. So by the time we become expert with this upcoming shells problem-solving approach, we're actually going to be able to derive velocity profiles like this, so long as we assume and only care to look at fluid flow situations that are 1D. So if we anticipate having a 1D flow, you're going to be able to actually derive what these functions are. So we've now talked about what it means for a flow to be 1D. Let's talk about what this new problem-solving approach of shells is. So I'm going to kind of divide up this page into two sections, and I'm going to talk about our new problem-solving approach of shells on the right-hand side. So what is this idea with shells? Well, the idea with shells is we have some part of our system that we're looking to derive a velocity profile and maybe some other information. So we're looking to derive a velocity profile and perhaps some other stuff that the velocity profile would enable. So up until this point, I'd like to contrast shells to these sort of macro control volume problems. So for macro control volumes, we often needed to be given in order to solve problems where we used some macro control volume. We needed to be given right. So for a lot of the problems that we solved so far in fluid mechanics, the clouds have opened up and Professor Landon's face has poked through and said, here is the velocity profile. The x velocity is a function of y, or the z velocity is a function of r. And then the clouds closed back up, and then we used this given velocity profile to determine things we care about. For example, like volumetric flow rates, external forces, etc. Right? So we were basically able to, if we were given a velocity profile, we were able to sort of make connections between details of this velocity profile and sort of macroscopic quantities, whole system level properties like the volumetric flow rate or forces on the entire system. Let's contrast this to shells, whereas shells we're looking to derive a velocity profile. So we're not going to rely on the crutch of someone else having given us a velocity profile. We're now going to stand on our own two legs and be able to derive what this velocity profile is ourselves. And then we can go ahead and use it if we wanted to get some of these details like volumetric flow rates or external forces. But the idea here is we're looking to derive a velocity profile, not just be given it. So what might shells look like? Well, let's say I had, two solid plates, and I was applying some pressure to drive flow between those plates. I might end up with a velocity profile. Let's say I don't know what this velocity profile is coming out of it, right? So, there's some hypothetical velocity profile that I don't know what function describes this velocity profile. So what do I do when I'm doing a shells type problem? I break up my system, and rather than defining a control volume that sort of goes around the entire system, for shells what I do is I slice up my control volume I slice up my system into a bunch of mini control volumes. So these shells are basically these mini control volumes. And these mini control volumes have what I'll call a delta dimension. And the delta dimension basically is one dimension, one sort of length of part of the surface of one of our mini control volumes, and the delta dimension is the dimension along which we anticipate flow varying. So for example, if I had a coordinate system that was x and y right here, I might be looking to derive Vx as a function of y, and I would choose my delta dimension y of my control volume. I would choose my delta dimension to be the dimension along which flow varies, right? So our x velocity is going to be a function of y, so I choose my delta dimension to basically be this. And some of this will make a little bit more sense once we get to the example problem and how it actually plays out. But the key thing here is we rather than defining a control volume that sort of circumscribes the entire system, we're filling up our system with a bunch of mini control volumes where there's a delta dimension, a sort of infinitesimally small dimension that corresponds to the direction, the coordinate along which we anticipate flow varying. So that's this idea of shells. And the idea with shells is, and then we can apply some further analysis to this control volume that I'll talk about later on when we define the steps for shells problems. But the idea here is we're carving up our system into a bunch of little control volumes, and this enables us to derive the velocity profile. And deriving this velocity profile, we need to be given a whole lot less information, right? So here we only need to be given, for example, like properties of the fluids. For example, like its viscosity and its density, and the geometry of our system. For example, like what is the whole height of this channel, something like that. And we also need to be given what are called boundary conditions. For example, maybe what the x velocity is at the top and bottom. So, compared to being given an entire velocity profile, we're given a heck of a lot less information for these shells types problems, and we sort of pull ourselves up by the bootstraps using this very limited information to derive a velocity profile. And we can sort of contrast this to these macro control volume problems where, for example, we sort of drew a control volume maybe around the whole system. We were given an information about a velocity profile, and maybe we derived, what the volumetric flow rate was, or something like that, right? So so these approaches are complementary in some problems, but distinct in terms of what our goals are. So, thus concludes this idea of this new problem-solving approach of shells, where instead of defining a control volume around our entire system, we essentially build up a block of, hypothetically infinitely many mini control volumes where they have a delta dimension that corresponds to the coordinate where we anticipate flow varying. And this allows us to derive a velocity profile. And that's something that macro control volumes can't give us. So now that we've sort of broadly described one-dimensional flows and what makes flows one-dimensional, and broadly described how this shells approach differs from the previous problem-solving approaches we had of macro control volumes. Macro meaning it sort of covers, it's a macroscopic control volume that covers our entire system. Now let's proceed with setting up the specific problem that I prefaced at the start of this lecture, talk about some goals, talk about what information needs to be known, and we're essentially going to use shells to derive the velocity profile of the fluid that was, of the blood or fluid that was streaming down that inclined surface. So let's set up our blood oxygenator problem. So let's look at a side view of our inclined plane blood oxygenator. So imagine I have this ramp. I'm kind of looking at it from the side. And I have some blood that's flowing down the ramp. And, near the top, I kind of have some kind of goofy flow profile as the pump sort of carries the fluid over the top. But eventually the flow kind of settles into a film of constant thickness that travels down the ramp, and then kind of has some goofiness at the bottom where the pump sort of takes it back in and puts it back at the top. So so we sort of have this system right here. And, we might, for example, imagine that, if I'm looking at this in a side view, this whole system is sort of extended a width W out of the page. I might imagine that gravity is pointing down like this, right? And gravity pointing down essentially is what's pulling this fluid down the top of the ramp. I might say, hey, this ramp makes some known angle with the ground, with horizontal, that I'll call alpha. Right? So there's some angle alpha that the ramp makes with the ground. And there's some, let's say, length of the ramp, some long length of the ramp, L, that's known as well, right? These are all things that I could measure. I could take out a ruler and measure these things, or a protractor and measure that. I know what G is, right? Let's also assume that we know some properties of the fluid, and I know what you're saying. Hey, Professor Landon, earlier in this class you gave us a lecture telling that blood was a non-Newtonian fluid, and it is. But for the purpose of simplicity and explanation, let's just assume that we have a blood of some known constant density and constant viscosity as well. So we're assuming essentially that blood is uniform and Newtonian, which, strictly speaking, it's actually neither of these things. But again, for simplicity, let's just assume that it is for this problem. Let's assume that we have the blood film with some thickness H. And we're essentially looking to figure out, what is the velocity profile of the blood as it trickles down this ramp. So we might anticipate, broadly when I'm looking to solve these problems, I kind of like to sketch out, even though I don't necessarily know exactly what function is going to describe the velocity profile in this. I like to sketch out what the velocity profile might look like. So I urge you to pause and ponder. Sketch what you think the velocity profile will look like. Where do you think the velocity is going to be fastest? Where do you think it's going to be zero? Is the velocity profile going to be linear or curved? Take a moment. Guess what you think the velocity profile is going to look like down this ramp. All right, hopefully you've had a chance to pause and ponder. I'm going to do the annoying thing where the professor already knows the answer, so we can sketch it out very easily. So we anticipate the velocity being 0 right at the surface here, because the ramp isn't moving, so the fluid immediately adjacent to the ramp is not going to be moving. And we expect that the farther we go away from the ramp, the faster the fluid is going to get. So it turns out we actually, spoiler alert, we're going to get a parabolic velocity profile where the maximum occurs right at the surface and the velocity kind of tones down as it gets close to the ramp and eventually has 0 velocity right at the surface of the ramp. So this is this velocity profile that we're looking for. Now, and so that's basically our goal, right? So if we're defining our goal is, so one of our goals, our first goal, is to derive And if we're going to derive this velocity profile, we should do so, spoiler alert, we're only going to be able to do so in the framework of it being one-dimensional. So, pause and ponder again. Define a coordinate system. Define a coordinate system where we will be able to derive this velocity profile. Define a coordinate system that makes this flow 1D. All right, so what are the characteristics of 1D? We want flow moving in only one direction, and we want that flow varying only in some other direction. So what does that mean? Well, a lot of times we might want to define a coordinate system that sort of aligns with gravity because that's convenient in a lot of cases, but that's actually not the case here, because if we define a coordinate system like this, then but our flow is sort of pointing down the ramp like this, then we would have both x and y components to our velocity. So let's not define our coordinate system like that. Instead, let's define a coordinate system where y sort of starts at the bottom of the ramp and points up, and x starts at the top of the ramp and kind of points down. So x is sort of the direction of flow, and y is a direction in which we anticipate flow varying, with zero flow at y equals 0, or zero velocity at y equals 0, and a maximized velocity for y right at the surface there. So in this case, we're looking to derive a velocity profile. So what do we want? We want v sub something as a function of something else. So pause and ponder. What do we want? Well, we want a velocity in the x direction that is a function of y. So this is our goal. Our goal is to derive this velocity profile, and that's going to be this right here. So we're looking to derive this vx as a function of y. Once we have this vx as a function of y, what are some interesting things that we can do with it? We can actually get the distribution of shear stress in the film of moving blood. And in this case, the shear stress is going to be tau yx, and spoiler alert, this tau yx is actually going to be a function of y as well. So we're going to have this distribution of shear stress. Take a moment now and think, why might we care about why might we care about what the distribution of shear stress is for this blood? Who cares, right? Who cares about shear stress? Why do we care about shear stress in blood? Well, it turns out that shear stress is actually very important for blood, particularly this blood oxygenator, where we take blood out of a patient, oxygenate it, and then attempt to put it back in that patient. It turns out that if you put blood under too much shear stress, you start tearing open a lot of the blood cells, and in particularly platelets. And basically, if you start tearing open platelets, or even just applying so much shear stress that you activate them, you cause clots. And you can imagine if I had some blood oxygenator that took blood out of a patient, put too much shear stress on that blood as it flowed down the ramp, got it full of clots, and then pumped that clotted blood, tried to pump that clotted blood back into the patient, that could be huge risks, right? So we're in the business, as bioengineers, we're in the business of keeping people alive, not killing them with our devices, right? So we care a ton about keeping shear stress on the blood low enough. And with our newly gained skills in fluid mechanics, we can predict, safe levels of shear stress for the operating conditions of our device. Finally, one thing we might want to be able to do is, if we have this velocity profile, we might want to derive the volumetric flow rate. We might want to basically predict, what is the volumetric flow rate for this device, right? And you could imagine, if I had a relationship between volumetric flow rate and all of these known given parameters, that would be super useful, right? Because then I can basically say, hey, if you pump up blood with this volumetric flow rate, then I'm going to get, this type of velocity profile, this type of shear stress, this thickness of the film at this angle of the oxygenator, right? So if I have a relationship, if I can predict the velocity profile, then I can use that to get the volumetric flow rate in terms of all of these known parameters, and that's useful for sort of setting the operating conditions of our device. So this is our goal. This is the problem we're trying to solve as bioengineers. So what's our approach? What's going to be our strategy for solving this problem? So let's lay out the steps for our general approach to shells problems. So the first thing is after laying out the problem information that we did just a moment ago, so after we've done that kind of step 0 of sort of sketching the system and collecting together all of our known parameters, the next thing that we do is to select or define an appropriate shell. And in a sense, this is our micro control volume. The next thing we do is apply conservation of mass to the shell. And oftentimes what this does is affirm the 1D-ness of the flow. The third thing that we do after we've applied conservation of mass to the shell is we can apply conservation of momentum to the shell. And oftentimes when we do conservation of momentum to the shell, we might need to actually apply conservation of momentum potentially in along multiple coordinates or in multiple directions. So for this problem, we're going to need x and y momentum to help solve us. Right? So we're going to need conservation of momentum, possibly multiple directions, and basically what this is going to do is this is going to help us set up a differential equation. This is going to help us set up a differential equation, and once we get to this point, I'll clarify, what differential equation we're actually talking about. A differential equation with derivatives of what with respect to what. You sit tight. We'll get there later on. Then the next thing that we do after applying conservation of momentum to the shell is we apply a constitutive relationship, so a relevant fluid So what do I mean by constitutive relationship? For example, for Newtonian fluids, it was tau yx is equal to minus mu d vx dy. So we have this constitutive, with this constitutive relationship right here. So momentum balance, will essentially rope in shear stress into this equation, and then we'll, relate shear stress to velocities here. Then what we're going to do is we're going to, this will help kind of build up, after we apply this constitutive relationship, then we'll end up with a differential equation. So we'll basically combine the makings of a differential equation with this constitutive relationship, and we'll get a differential equation for velocity. And once we have a differential equation, we'll need to solve that differential equation. So the next step, after we apply this constitutive relationship, is we're going to compute the velocity profile . we're going to compute the velocity profile by integrating to solve this differential equation. And once we've integrated to solve that differential equation, then we will, once we've integrated to solve this differential equation, spoiler alert, if you remember, when you integrate, you're often left with constants or spoiler alert, maybe even functions of integration when you integrate to solve stuff. And it turns out that the way you resolve the sort of extra unknowns that you get when you integrate is you apply boundary conditions. So we need to compute the velocity profiles by integrating to solving the differential equation and applying boundary conditions. Then once we've done this stuff, we finally have derived our velocity profile. Woohoo! But we don't necessarily pat ourselves on the back at this point. So for example, for our blood oxygenator problem, we're not looking to just rest on our laurels with having derived the velocity profile. We're also looking to, get shear stress and get this volumetric flow rate. So generally the last thing we might do in shells type problems like this is use our velocity profile to compute quantities of interest. For example, shear stress or volumetric flow rates, etc. So this is our general approach to solving shells problems. And for the remainder of this lecture, I'm going to go through the first two steps, and then in the next lecture, I'll go through the remaining steps. So let's proceed with step 1. So before we go ahead and define shells, I often like to sort of put the shell, sketch what we anticipate the shell being in the context of the system, right? So we have our ramp that's going down, we have the surface of the blood on top, and we'll define a shell to be somewhere in the middle. So some tips for defining a shell is oftentimes we choose two delta dimensions. One of the delta dimensions will be the dimension or along the coordinate where we expect flow to vary. So in our case, we're going to choose y is the coordinate. So the delta dimension will be, so basically one of the dimensions of our shell is going to be delta y. And then usually another one is along the direction of flow, and this one will basically help us confirm the 1D-ness of the flow. So in this case, we anticipate the direction of flow to be in x, so we're going to choose delta x as one of our delta dimensions. So what does it look like? Well, if I have some control volume where the one of its delta y and one of its delta x. It's sort of a little chunk that's kind of just chilling in the middle of the flow. We're going to make this sort of infinitesimally small, but I've sort of drawn it big enough so we can actually sketch what it looks like. This thing, it basically has a height delta y and a length delta x. But of course, a control volume isn't just a rectangle like this. There's actually some 3D-ness, right? A control volume is an actual whole volume, right? So there's this dimension out of the page, and generally, you only really need two delta dimensions. Your third can be a macro dimension. So in this case, if we go back to the problem statements, this whole system has some width w out of the page, and basically nothing varies in z. If it's sort of x, y like this, we're assuming nothing varies in z along the whole width w of our device. So in this case, since nothing interesting is happening into or out of the page, right, all of the flow is essentially in this direction here, we can basically just make the third dimension of this control volume sort of a width w that's extending out of the page like this. So in this case, w for us. Oftentimes, when we have this control volume here, it's useful to characterize a couple of properties of this shell. So I'm going to ask you to pause and ponder and work out three characteristics of the shell. So pause and ponder. Three things. What is the shell volume? What is the area of the top? What is the area of the top face of the shell? This one right here. And what is the area of the upstream face? Which I'll highlight in yellow right there. So take a moment, pause and ponder, and work out what those three parameters are. So hopefully you've had a chance to work it out. In this case, the shell volume would just be the length times the width times the height. So in this case, it would be delta x times delta y times w. The area of the top face would basically be delta x times the w. It would sort of be this like top, like if it were a box like this, it would be the top. And the area of the upstream face would be, this dimension delta y times the dimension out of the page. So it'd be delta y times w. And keep these bookmarked. We'll come back to them in upcoming steps. So thus concludes step 1, where we define the shell. Now let's move on to step 2, where we apply conservation of mass to it. So before we get too deep with conservation of mass, I want to go back to our problem statement. And when we're solving problems like this, we've already made a handful of assumptions, right? A couple about the properties of the fluid and a few more in other places. I like to just keep this list of all of the assumptions that we've made so far. So in this case, the assumptions that we've made so far, we haven't really invoked these, but we haven't made it yet. But so far, let's assume that we have flow in only the x direction. So we have flow only in the x direction. So let's assume this, and let's also assume that our system is in steady state. Right, it's not like I'm turning on and turning off the faucet, or like twiddling my pump flow rates to go higher and go lower and something like that. You know, once the system sort of starts running, we kind of establish some velocity profile that if I took a snapshot and then came back later, the nature of the velocity profile wouldn't have changed, even though there might be different molecules of blood flowing down it. So, so with these two assumptions, you know, let's move forward. Oh, and I guess we're also going to assume that density is a constant for this next step. So let's make these assumptions and proceed with conservation of mass. So if we apply conservation of mass, we end up, we have d dt of an integral over the volume of rho dv equals minus an integral over the surface of rho times v dot n dA. And if we look at our left-hand side, well, this term can basically go away because we're in steady state. Steady state. For the second term here, let's number our surfaces. Right? So let's say let's apply conservation of mass to our little chunk right here. We'll number our surfaces. We'll say 1 is this upstream surface right here. We'll say 2 is the downstream surface. We'll put 2 right here. Then we'll make 3 this bottom surface right here, and we'll make 4 that top surface right here, which kind of corresponds to those up there. And so this is going to be our control volume, and we've sort of numbered those surfaces. So how does that help us? Well, the idea is even though flow varies in y, we can choose to make delta y arbitrarily small. Right? And in fact, like in a calculusy way, infinitesimally small. And if we choose to make delta y arbitrarily small, I mean, we could also make delta x arbitrarily small if we wanted to, but let's make delta y arbitrarily small. If we make delta y arbitrarily small, then for our calculusly small control volume right here, flow will not vary across or sort of within any face. Flow will not vary within any face of our control volume. And there's a little bit of some kind of reasoning that I'm sort of glossing over and skipping over a little bit in sort of in the interest of, you know, not being totally rigorous. So the flow will not vary within any face of the control volume, but can vary on opposing faces. So what do I mean by this? Well, let's basically say, hey, on this surface here, on surface 1, let's say we have some Vx at position x, where we call, let's say we call the location of this face position x. Then if we wanted to describe the position of this face, I would describe the position of this face as x plus delta x, right? Because basically the this length of the control volume is delta x, right? So I might say, hey, I have some Vx at position x, and I'm, just for the time being, neglecting the fact that Vx varies across face 1 because I can make this arbitrarily small. But I'm allowing for the possibility that Vx is different at x than it could be at x plus delta x. And again, I know this is a little circular. I know this kind of leaves some like potentially frustrating mathematical loopholes, but just bear with me. This is what we're going to do, and the math people have given me, a handwritten and stamped of approval that this works, that the calculus works. So we're basically going to say, hey, these two velocities could be different from one another, but we're neglecting any velocity variation on a particular surface. So this is the plan. So now we're going to apply conservation of mass. So if I'm applying conservation of mass to this thing right here, take a moment now to pause and ponder. Do I need to include any other velocities going on? So for conservation of mass, do I need to include any other velocities? Well, not really. So we basically said if we go back to our assumption that flow is only in the x direction, if there are x velocities on this surface, they wouldn't contribute to flow into or out of the surface because v dot n would be 0, nor would any x velocities on this surface. And if we said velocities only in the x direction, then we don't have any y velocities that could be contributing to mass entering or exiting through these surfaces. So we basically said, hey, there's no y velocities, and the x velocities only really matter for surfaces 1 and 2. So that's it. So now we can proceed with evaluating this, this integral right here. So take a moment now, pause and ponder, see if you can evaluate this surface integral for this system right here to apply conservation of mass. All right, hopefully you've had a chance to pause and ponder. So left-hand side is 0. So we get 0 equals minus the integral over surface 1. V dot n for surface 1. N is pointing to the left, right? N is our outward pointing normal, and it's pointing in the opposite direction of Vx at x. So we have the integral over surface 1 of rho, which is a known constant, times Vx at x. Vx at position x, dA. And then we have minus the integral over surface 2 of rho Vx at x plus delta x. dA. And we safely concluded that v dot n was 0 for surfaces 3 and 4, so we basically have minus 0 and minus 0. We can of course make progress with this. Remember we said that flow will not vary within any face of our control volume, so that means we can basically pull these integrals out, and we already assumed that rho was incompressible, so we could pull those out. And when you do that, oh, hold on a second. What did I forget here? Forgot a minus sign, right? Vx is pointed this way and n is pointed this way for surface 1. So the v dot n should be minus Vx at x for this surface. But it's positive Vx at x plus delta x for that other surface. Got it. All right, so what do we have here? We have 0 equals, we can divide out density from both of these terms. So we're basically left with 0 equals Vx at x times the integral over surface 1 dA minus Vx at x plus delta x times the integral over surface 2 dA. We can of course replace these with the integral over surface 1 dA is just the area of surface 1. And if we go back to the area of the upstream face, that's delta y times w. So this is going to be delta y times w. And as would surface 2, right? Because surface 1 and surface 2 are basically the same, they have the same areas. So what does that leave us with? This basically leaves us with 0 is equal to minus Vx at x plus delta x minus Vx at x. And I'll tell, it'll make sense in y in just a minute why I sort of multiplied everything by -1 and rearranged some orders, times delta y times w. All right, now, so we have some results. The implications of this result we haven't quite gotten to yet, but I'm going to apply a trick that is basically, that we're basically going to do almost every time in these problems, anytime we apply conservation of mass to the shell, and later on when we apply conservation of momentum to the shell. The thing that we do once we get to sort of this point like this, where we have, you know, some v's and some deltas or some other quantities of interest, is we divide by shell volume. So if we divide by shell volume, we calculated that earlier, delta x delta y times w. So what do we get? We get 0 is equal to minus Vx at x plus delta x minus Vx at x times delta y times w. We divide it by shell volume, which we said was delta x times delta y times w. We get some interesting cancellations, right? So we get some helpful cancellations. These cancel, these cancel. So take a moment now, pause and ponder. What is the sort of meaning, or what is this thing that we have left here? You know, what does this mean? Does this look familiar in some way? You know, what's going on here? Well, if you dust off your high school calculus, this is essentially the definition of a derivative with, I guess, a minus sign out front, right? So in this case, we basically have 0 equals minus the derivative of x velocity with respect to x. Now, we need to be a little bit careful with this derivative, right? So this is essentially the definition of a derivative. But the tricky thing with Vx is, you know, in general, Vx could be a function of x, y, z, and t, so it has derivatives with respect to any of these variables, right? So hypothetically, there could be some partial derivative of Vx with respect to time, some partial derivative of Vx with respect to x, some partial derivative of Vx with respect to y, and some partial derivative of Vx with respect to z, right? So hypothetically, there are all of these partial derivatives because Vx could vary with x, y, z, and time. And when we have some function that could be a function of multiple variables, we need to worry about there's not just a derivative with respect to one of them, there are derivatives with respect to a bunch of them, and the partial derivatives acknowledge the idea that they could vary with respect to multiple variables. In this case, we have this thing right here, this Vx at x plus delta x minus Vx over delta x, and basically what this means, what this gives us is in the limit as delta x goes to 0, this finite difference becomes a partial derivative of Vx with respect to x. So, you know, in calculus, in Calc 1, you know, we were basically talking about functions of only one variable, where this would have given us, you know, the normal dvx dx. But because Vx could hypothetically be a function of all these things, in this sense, it produces a partial derivative. So what does this mean? Well, if based on this result from conservation of mass, conservation of mass tells us that Vx is essentially not, if that dVx dx is 0, and if dVx dx is 0, that basically means that Vx we can conclude is not a function of x. So in general, Vx could be a function of all of these things, but from our result from conservation of mass, we can basically say, hey, in this case, it's actually not going to be a function of x because we safely concluded, because conservation of mass told us that dVx dx is 0. And basically, if you have some Vx that's not a function of x, when you take its partial derivative with respect to x, you're treating everything like everything else besides xy like things as a constant. So you're essentially taking the derivative of a constant, and that's 0. So conservation of mass essentially tells us that Vx is not a function of x because its partial derivative with respect to x is 0. So what does that mean? We can safely conclude that Vx is not a function of x. We basically already said that Vx isn't a function of time because it's steady. And in our problem statement, we were sort of assuming that nothing varies in z. So if we sort of add this to the sort of more explicit no z, if we add no z variation to our explicit list of assumptions that we're making here, that's just equivalent to straight up assuming that Vx is not a function of z either. So what does it mean? Conservation of mass basically told us that Vx isn't a function of x. Our assumptions, no z variation, told us Vx isn't a function of z. And steady said it isn't a function of time. So this conservation of mass, this whole process, basically allowed us to sort of affirm our belief. So this affirms that Vx is a function of y only. And if Vx is a function of y only, then we've successfully done our 1D, one-directional, then we've successfully described this as a 1D flow. So it's a little bit circular, but we've everything is in order. We can safely, we feel this just affirms how safe we can feel about our shell's approach for this problem. So thus concludes our application of conservation for mass, and this affirms the 1D-ness of the flow. So that's where we're going to stop for this lecture. For upcoming lectures, we're going to proceed with the remaining steps for this problem. So sorry to leave everyone on a cliffhanger, so stay tuned for next time. Thanks for watching, and good luck with your studies of fluid mechanics.